Hi, and welcome to Chapter 5.3, Atomic Emission Spectra and the Quantum Mechanical Model. In this picture we see a typical neon sign advertising hamburgers. Some of you might really like that. What's happening is electricity is going through these tubes that are filled with neon gas or one of the other noble gases, and it makes the gas glow with its own characteristic color. Now, what causes this atomic emission spectra is what we're going to answer in this video. So if we look at light we think of as a wave that travels, and we've got several things to define about light in this picture. We see a wave, and we see several things on this wave. Okay, we're going to see, let me go back. We see on this wave, we see a amplitude, which is the height of the wave, which we're going to basically say the amplitude here is the height from the midpoint up to the top. It would also be from here to here. We also have something called the wavelength. The wavelength is the distance between two peaks. So wavelength is symbolized by this Greek letter called lambda. So lambda is a Greek letter that represents wavelength, okay? And it's between crest or trough and trough, all right? Amplitude is from the zero position up to the top or down to the bottom of the wave, okay? So that's amplitude. The next thing we want to talk about is frequency. That means how often do these crests appear, okay? And frequency is represented by another Greek letter. This Greek letter is called nu. If we can get that. Okay? And it's basically the number of cycles that pass at a given point of time. Now, usually it's per second, but to make it easier, we came up with this unit called hertz. Okay, the nature of light. The product of frequency and wavelength equals a constant c, the speed of light. C equals wavelength times frequency. So in this slide, we have c, which is the speed of light, lambda, which is wavelength, and nu, which is frequency. That is how we determine this value. So here we have speed of light. Okay, and we have nu, which is frequency. And we have wavelength. Okay, the frequency and wavelength of light are inversely proportional to each other. Okay, so in other words, in this first red section, we have a wave that has a very low frequency. You don't see a lot of crest at the same period of time. Okay, both of these waves have the same amplitudes, but their frequencies are different. So this is a very low frequency. This one has a lot more crest, so it is much higher in frequency. You're going to see a lot more waves or complete cycles in a high frequency situation. Just so you know, a high frequency situation also has a lot more energy than a low frequency situation. This is one of the reasons why they used red and blue. Red is a lower energy wave, and blue-green is a higher energy wave. So what is light? Light is a waveform that we've already said that, but it's part of what's called the electromagnetic spectrum or electromagnetic radiation. Okay, other things that travel at the same speed as light are radio waves, microwaves, which you know from your ovens, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. Now, light travels at a set speed. Now, they're showing you here an example where we had 4 sig figs. A lot of times, we will round this number off to 3.00 times 10 to the 8th. So if you want to do a quick calculation, you can use that. And most of the time, we will use that. Okay, 3.00 times 10 to the 8 meters per second, which is the same, which is very, very fast. For instance, it takes about 9 minutes to get from the sun to the earth. Okay, the sun and other light bulbs, incandescent light bulbs, which are going out of style now because of energy considerations, they use up a lot of energy, emit white light, which is basically a light that contains all the wavelengths and frequencies of the rainbow. Okay, when sunlight passes through a prism, we break it apart and we see the spectrum of colors, which are the spectrum of the rainbow. In the visible spectrum, red light has the longest wavelength and the lowest frequency. The electromagnetic spectrum consists of radiation over a broad range of wavelengths. We start down in the red range, which is 700 nanometers. Now, if we remember when we were looking at our values that we converted using factor label, a nanometer is 10 to the minus 9 meters. So this is a very, very small amount. We're talking in the range of the size of atoms or molecules. And it goes all the ways up to, that's the big wavelength, and it goes down to 380 nanometers at the violet level. That's visible light. If we look down to the full electromagnetic spectrum, we see that the visible light is only a very, very small part of it. We see very, very long wavelengths for radio waves. Now, this kind of makes sense because radio waves travel a long distance and you can hear them on your FM radio station or AM radio station. And so they have very, very low frequency so that it travels a long distance. Then we have radar is the next. It's a little bit shorter, okay? And that can travel a long distance. We use that to look at planes. Microwaves, your cell phones are using microwaves, okay? Then you have infrared, which is getting closer to the visible spectrum, but it still is, you can feel the heat in an infrared ray, but it's basically a much lower frequency ray than light. Then we get to these rays that are high frequency. First is ultraviolet, and you know from going out in the sun that you have to wear sunscreen no matter what level of coloration your skin may have. You still can actually be affected by the ultraviolet rays. Some people are very, very, very sensitive based on their lack of melanin, and other people are a little bit tougher than that, but everyone is susceptible to ultraviolet rays. Next, we have X-rays, which can go through your body. They can penetrate through your body, and that's why you can see your bones when you do an X-ray. And the most dangerous rays are gamma rays, which have very high frequency radiation, which can go through our bodies and the cells in our bodies. So basically, these are relatively safe on this side, and these get progressively more harmful to us as time goes on, as you get more and more frequency. So that's the electromagnetic spectrum. The speed of all these waves are 3 times 10 to the 8th meters per second. Okay, now, when atoms absorb energy, their electrons move from a lower energy. You think of that ladder that we saw in a previous section. We had a ladder. And remember how that ladder, the rungs were not quite the same? As we went up the ladder, the rungs got closer and closer together. Okay? So to go from here to here, we have to basically add energy. Okay? But this usually is not the stable place. We want to be at the ground state, so they will fall back. So it absorbs energy, and then it falls back, and it emits electromagnetic radiation, or light. Okay? It can be ultraviolet, it can be infrared, which we don't really see. We need instrumentation to see those emissions, but we can see visible colors, and that is why we have different colors for different atoms. So here's a picture of what a prism does. We have a slit that we shine light through, go through a prism, and the white light is separated into the colors of the spectrum or the rainbow. Okay, instead of using white light, if we use a lamp that only has one substance in it, such as helium, we see a kind of a different picture. We saw the whole rainbow with white light, but here, using helium, we're seeing a partial spectrum. We're seeing lines here, 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 and here. This is like a fingerprint. It's unique for each element. Okay, so we can use this information to identify different substances if we have different types of lamps. So the light is shown on this cardboard and goes through the slit, and then it breaks apart, and this is what we see. So all that black lines are things that it's not emitting. Okay, so what happens is we have helium here. We put this into some electricity. We get it excited, and then as it moves from a higher energy level, it gives off, and down back to the lower energy levels, it gives off light. And this can be predictable based on the substance we're looking at. So to summarize, the energy that's absorbed to move it up into a higher energy level is equal to or identical to the energy of the light emitted, okay, when it goes back down. Okay, these emissions make spectral lines which are characteristic of the element. Okay, that's what we saw with helium. And we call this atomic emission spectroscopy, or this is called the atomic emission spectrum of the element. No two elements have the same emission spectrum, so it's a fingerprint. All right, so now I'm going to walk you through how to calculate wavelength or even frequency if you know information and know your equation that we looked at earlier in the slides. So we have a yellow light. It has a frequency of 5.09 times 10 to the 14 hertz. Hertz basically means a reciprocal second, or the number over s, okay, or s to the minus 1, whatever way you want to write that. But we use hertz to stand for frequency. It means there are that many waves in a second. That's basically what hertz means. There's that many waves. 10 to the 14 is a huge number, so this is a high frequency wave. Okay, so it's yellow. So if you think of your spectrum as Roy G. Biv, where does yellow come? Red is the least energy, so it's like the third from red, so it's getting to be higher. Okay, so what do we know? We know what the frequency is, and we know what the speed of light is. If you don't remember 2.998, you can always use 3.0, and so you can use 3.00 times 10 to the meters per second, second, and this to the eighth. Okay, and we want to know wavelength. So we look at our equation, C equals wavelength times frequency. We know C. We know C, and we know this, we want to find this. So we are going to divide both sides by nu, okay, as shown in this slide. So our new equation is wavelength equals c over nu, or c, speed of light divided by frequency. We substitute in the information. Notice how we changed hertz to seconds, so the seconds cancel out, because where do we get that reciprocal seconds? We know that wavelength is in meters. So if we want meters per second is the speed of light, then when an initial equation, if we go back to that, we have to get meters per second. So wavelength is meters and frequency must be some number over seconds. That would give us meters per second. That's where the hertz comes from. Okay, this makes sense? So in other words, if we rewrite this, 1 hertz equals 1 over s, or 1s to the minus 1. You can write it any of those ways, it means the same thing. But make sure you know that hertz is equal to 1 hertz is equal to 1 over s. That will help you always get the right labels when you do these calculations. Okay? All right. Now the magnitude of the frequency in this case was a lot larger than the speed of light, because the speed of light is 3 times 10 to the 8th, whereas the frequency is to the 10th to the 14th. So it's going to be a very small wavelength, which makes sense because it's a high frequency. So the distance between crests should be smaller, and we're going to report it to 3 significant figures because that was what our frequency was in. Okay? All right, now it's your turn to try it. Okay, so I'm going to give you this question. I want you to calculate it, and you'll answer it on play pause it. Okay, so give me a second. All right. So again, you use this equation again, c equals wavelength times frequency. We want to solve for frequency this time. So we divide speed of light by wavelength, okay, and we basically take our 2.998 times 10 to the 8 meters per second and divide it by our wavelength of 6.76 times 10 to the minus 7. Now, where did that come from? Okay, so let's look at that. What is a nanometer? So I would probably have written it this way to start with. I would have wrote 676 times 10 to the minus 9 meters, because nanometer means 10 to the minus 9. And then if I wanted to make it scientific notation, okay, I bring that over and get 6.76 times 10 to the minus 7 meters, okay, because basically what I did is I divide it by 100, so I have to increase this by 100. Now it's going from 97. Why is it going to the lower number? Because actually this is a bigger number because we're talking negative numbers. Okay? Now, I want to talk something next about something called the photoelectric effect. Einstein came up with this idea. And basically Einstein said that there are times when waves act like particles, and when particles act like waves. Okay? And since we're talking about waves when we talk about light, we're talking about sometimes these waves act like particles. Now, in everyday life, most things that we consider waves act just like waves, the typical physics that we learn there. But when we get to very, very small things like the atom and electrons and protons and neutrons, then weird things start happening. And that's where Einstein comes in with his ideas about physics at the very tiny level. Okay? So first thing we're going to talk about is the photoelectric effect. Okay, there was a gentleman named Max Planck, and he was able to figure out that the energy of a quantum, okay, that was absorbed or emitted by a body is proportional to its radiation, okay? Frequency of its radiation. So he basically said energy is proportional to frequency. So the higher the frequency, the higher the energy is what he's saying. And he was able to come up mathematically with a constant that could turn frequency into a unit of energy. So if we look at this equation, E is energy. We already know that's frequency. And this is something called Planck's constant. Okay? And so this Planck's constant has a value of 6.626 times 10 to the minus 34 joules times second. Okay? Joule is a unit of energy. The reason it has a second is because if you multiply that by a frequency, the s's, or the seconds, will cancel out. Okay? So this is a very, very important idea of how we determine the energy of what we're calling a quantum, because a quantum is a little packet of energy. Remember how we said in the last area that to go up the rungs of the ladder, we needed a discrete amount of energy called a quantum? This is what we're talking about now. So Einstein used Planck's quantum theory to explain what is called a photoelectric effect. Okay, a photoelectric effect means that if I shine a light on a piece of metal, so here's some light, here's some metal, okay, some electrons will start being pushed off the metal because it gives enough energy to whoosh those electrons away. Okay? Light's doing that. So if you think about it, it's kind of weird because it would make sense if we were taking like a billiard ball and hitting something and then making a chip come off because we actually have a collision. Okay? In this case, we're talking light, which we think of not as a particle, but because electrons are so small, light is acting like that big billiard ball and pushing those electrons off the metal. Okay, now, you have to have enough energy to do this. Okay, for instance, red light is very low frequency. And so if you shine it on something like potassium, no matter how intense it is, how bright that light is, if it's red light, it will not remove an electron. When you get up to the yellow range, now it's starting to have enough energy that it can actually begin this photoelectric effect. Again, classical physics, this is very important. I kind of said this earlier. Classical physics says that light waves should not be able to do that. Okay? So classical physics describe light as a form of energy. And energy is not a particle. Okay? So for macro systems, everyday systems that we look at, like chairs, if I shine light on a chair, it's not going to move. Okay? But it assumed that under weak light of any wavelength, an electron in a metal should eventually collect enough energy to be ejected. Okay, so it's saying that, oh, if you kept on shining light on something, it would get hot enough that it would eject the electron. Well, that's not what the photoelectric effect is saying either necessarily. It's actually a little bit different. Okay? Okay, if you're shining a white light that has all the energies in it, maybe they could appear to do it, but that wasn't really the real reason. Okay, so if we go back and say light is like quanta of energy. So he kind of took Planck's idea and then said the light acts like particles. This is very, very important. Okay, and he gave them a special name. So light quanta are called photons. This tells us that we basically have we have photons, okay, and it acts like streams of particles that keep on hitting the metal, okay? But in other situations, life has wave-like form. So at very, very small particles, light behaves like matter, and when we're talking about big particles, like big things, it acts like a wave, okay? So we can go a little step further and think of things that are big. They also have waves, because we talked about my dance, okay? Things are vibrating, there's waves going on. But the wave forces, if we look at it that way, have a very minor role in things that are very large, and the normal gravitational forces are much bigger. Okay? Well, at the atomic level, the wave forces are much more strong or stronger because the things that they are touching are so small. All right, here's a really good picture, diagram of red light, green light, and violet light. We're increasing frequency from red to green to violet, and we see that in the waveforms that there's many more crests, meaning higher frequency. So in the red light, it's not strong enough. The frequency is not strong enough. Okay, the wave is weak, and so it doesn't emit any electrons. Once we get up to the green light level in the second picture, we see an electron is being ejected because there's sufficient energy in those quantum packets, those photon packets, to move it. And then when we get up to the violet light, it's going to basically be sufficient, but it's also going to transfer some of that extra energy into the speed of the electron as it moves farther away. So we have an effect of a threshold frequency which allows the electron to be ejected, and then we have a further effect that if we have extra energy, we can make the electron move faster. Then it acts as a thing to speed it up. Okay, so now we have another idea. We have another calculation I'm going to walk you through, is we want to find the energy of a photon if I give you a frequency of 3.20 times 10 to the 11 reciprocal seconds, or hertz. So we know two things. We know the Planck's constant, and we know the frequency, and we know our equation. So we're looking for in joules, so we just multiply the two together, and we end up getting 2.2 times 10 to the minus 22 joules. Does it make sense? Individual photons have very small energy, so the answer seems reasonable. If we look at it, that Planck's constant has a value of 10 to the minus 34. That's going to make it very, very small, which makes sense because a photon is not going to be sufficient to move you. Okay, so it's a very small amount of energy to move very small things. Okay, try this one to calculate the frequency of a photon whose energy is 1.166 times 10 to the minus 17 joules. Okay, same equation that we just looked at. Try it on play pause it. All right, so we have our formula. We want to find wavelength now, so we divide energy by Planck's constant, and we get an answer of 1.760 times 10 to the 16 over S, or hertz. Okay. Okay, how are the frequencies of light emitted by an atom related to changes of electron energies? Okay, the most stable form of an atom is have its electrons in the ground state. It's kind of like if you think of the Empire State Building. The ground floor is the bottom floor, and that's the most stable place to be. So that's our quantum number, n equals 1. Okay, so that's your first floor. Okay, so that's the ground state. Okay, if an electron moves up, it can move up to any of the higher levels from there. Okay, second, third, fourth, fifth, or sixth floor, or rungs of the ladder. Okay, a quantum of energy in the form of light is emitted when the electron falls back to the lower energy level. So it requires a quantum of energy to get up there, but that could be heat, for instance, or it could be energy incoming light. Okay, but when it falls back to the ground state, we're going to see light emitted. Now, sometimes light will be ultraviolet, and some will be infrared, which we can't see with the naked eye. We have to have another device to measure that, but we can see anything in the visible level, and we'll see different colors. Okay, so the light emitted by an electron moving from higher to lower energy level has a frequency directly proportional to the energy change of the electron. That's E equals hv. Now, we've got three types of lines that we can have. As I mentioned, we have the ultraviolet, the visible, and the infrared. Okay, and we have three different spectrums. Okay, so the one with the most energy is the one with the highest frequency, which would be the ultraviolet ones. So we have, that's called the Lyman series. Okay, the visible series is also called the Balmer series, and the infrared is called the Paschkin series. Okay, notice that we're going from higher frequencies to lower frequencies. Notice that ultraviolet always ends up at the 1 energy level, n equals 1. So it's dropping from higher to 1. So we don't usually see these with the naked eye. What we see with the naked eye is when it's going from to the second energy level. Okay? Second to third to second. Okay, 3 to second when it's falling from there. And then things in the infrared are ending up on the third level. So they're coming from higher to the third, higher to the second, and then higher to the first. So this is going to be our biggest distance, okay? And so if we look, for instance, compare 3 to 1, 3 to 2, okay, there's no there. If we did 4, we'll always see the highest one is when we compare electrons falling from the same energy level to the first, is always going to be the highest energy change, okay? Because it's the biggest difference. So as we go out, we see that these rings get closer and closer together, so the energy differential is not quite as large. Okay, so in that tube, we didn't just have neon, we also had the other noble gases, and each of those noble gases give off a particular color. I'll give you another thing though, most of these neon lights also, a lot of them are painted too, but they do have their own unique colors. Okay? Alright, so in the hydrogen spectrum, which of the following transitions produces a spectral line of the greatest energy? So is it when the electron comes from the second to the first, from the third to the second, from the fourth to the third? Okay, it's the same. We're looking at the same thing. All right, so which one is always the biggest? It's going to be, answer it. Yep, it's going to be A. It's always when it goes back to 1. If you see it going to n equals 1, it's going to have the greatest energy. Okay, how does it differ from classical mechanics, which is classical physics? Okay, I've talked about this a little bit, where I said the waves act as particles. Can particles of matter behave as waves? And yes, Louis de Broglie called wavelength behavior of particles as matter waves. And he basically led him to a mathematical expression for the wavelength of moving particles. So this helps us to understand how the electron behaves like light. Okay, and it helps us to understand a little bit about electricity too. Okay, so the wavelength properties of beams of electrons are useful in viewing objects that cannot be viewed with an optical microscope. This is what we do to see atoms. We use beams of electrons because they kind of are like waves. And they have much smaller wavelengths than visible light, and they allow for a clearer enlarged image of very small objects like pollens or other things that we can't see with a normal microscope. Okay, classical mechanics or physics describes the motions of bodies much larger than atoms, while quantum mechanics is used to describe the motions of subatomic particles and atoms as waves. Now, very important thing, this is not, if you've watched the show on TV that's over now, you heard of Heisenberg. Well, it's not the same Heisenberg. This Heisenberg was much older. Okay? The Heisenberg uncertainty principle states that it is impossible to know both the velocity and position of a particle at the same time. So you can't know both. And there's reasoning for this, because the tool in which you would use this is the same size as the electron. Okay, it's very, very critical when we talk about very small particles like the electron. But it doesn't come into play when you think of macroscopic things like cars and airplanes. Okay, so what happens is, if you want to locate an electron, you would hit a photon, throw a photon at it. Okay, it strikes the electron to observe the electron's position. Well, it might know where the electron was, but what the photon does, it then moves that electron away from that position. Okay, so now it's also impart some of its energy to it, so then it might change the speed of the electron. So it's very hard to know where the electron is or what velocity has been changed, okay? Okay, I just said this, so I'm going to give you this question. The Heisenberg uncertainty principle states that it is impossible to simultaneously know which two attributes of a particle. It's in play posit. Okay, velocity and position. Here are some of the important parts. Make sure you stop and take notes if you need to, and then here's your definitions that you definitely need to know. Okay, so the big idea for this section is electrons and the structures of atoms. Electrons can absorb energy to move from one energy level to a higher energy level. When an electron moves from a higher energy level back down to a lower energy level, light is emitted. So that's it. I'll see you later.